So we look at these couple of definitions. I think it's pretty straightforward in terms of what this is. Something that gets bigger or something that gets smaller every time. But in this case, we're talking about, individually increasing or individually decreasing, not like increasing and decreasing at the same time, which is the example of like a bouncing sequence that goes between -1 and 1 or -2 and +2, well, depending on how the sequence is defined. So in this case, we're going to show that this given sequence right here, n over n squared plus 1, it's a decreasing sequence. Well, number one way to look at this is, observe the denominator and see how the denominator is really larger than the numerator. So that means this is going to go decreasing, but that's not how we're going to show it. Another way is, plug in some values and see how the numbers get smaller and smaller every time. Well, that's not the correct way to do it. So plugging in values does not constitute a proof in this case. So what constitutes a proof in this case is something that works or that denotes universally at once for every single value of n. Well, how do we do that? Well, number one. So the condition for decreasing, which I'm going to write here, it's a sub n greater than the next term, a sub n plus 1, which you can see it in the picture, right? However, how do we apply this condition to a general rule such as this sequence? Well, so number one, let's identify a sub n, and a sub n is given, it's this n over n squared plus 1, and what would be a sub n plus 1? Well, in this case, a sub n plus 1, replace every instance of n with n plus 1. So for example, this n will be replaced with n plus 1, and this n that gets squared is going to be replaced with n plus 1. That is n plus 1 over n plus 1 quantity squared plus 1. So now, we're going to put these two expressions together in their corresponding side of the inequality. That is, we're going to write this n over n squared plus 1 and determine whether this quantity is indeed greater than n plus 1 over n plus 1 squared plus 1. Alright? So, let's see. Is that inequality true? At the beginning it might be deceiving because what do we have in the numerator? We have this n, but n is not greater than n plus 1. For example, is 5 greater than 5 plus 1, which is 6? That's not true, right? Or 7 greater than 8? Well, that's not true. Okay, but in this case, have a look at the denominator. Is the denominator on the right hand side bigger than the denominator on the right hand side? Well, essentially, this quantity n squared plus 2n plus 1 squared plus 1 plus 2, well, compare this quantity n squared plus 2n plus 2 with n squared plus 1. That's indeed bigger. So that means the denominator on the right hand side will be bigger, giving us a smaller quantity than that on the right hand side. So in this case, this is all we have to do and say yes, it's decreasing. That's how we show it's decreasing, not by a list of numbers and say, well, the numbers get decreasing every time. No, again, numbers do not constitute a proof or a show in this case. It needs to be a symbolic argument in this case. Alright, furthermore, we describe sequences, by their boundedness. So a sequence could either be bounded above or bounded below, or could be bounded both above and below. Well, how do we know in this case? Well, so we would have to look at a sequence, and in this case, find the limit of the sequence, but further look at the graph of the related function and determine whether that limit lies above the graph or below the graph. Alright, and in some cases we have functions that are, or not functions rather, sequences that have both a bound above and a bound below. And we're going to look at those special cases, and when when the sequence is both bounded above and below, we don't say it's bounded both above and below, we just say it's bounded. So the word bounded itself implies boundedness above and boundedness below at the same time. So let's investigate the boundedness of the given sequences right here. So number one, by the way, there's a little typo here. This is supposed to be 2 plus e to the negative n over 3. And starts at 1, goes all the way to infinity. So I forgot to type that plus sign. Alright? So, let's find the limit of the sequence. Limit 2 plus e to the negative n over 3 and approaches infinity. Alright, well, computing this limit, where is this term going to go to? 0, right? Well, I think I wrote the answer at the same time I could ask the question, right? So 2 plus 0, that's going to be 2. Well, that limit is 2. But in this case, we need to determine whether this limit is an upper bound or a lower bound. That doesn't tell us anything about it. So in this case, we would have to look at the graph of the related function. In this case, f of x equals to 2 plus e to the negative x over 3. So what do we have? We have an exponential function with a negative exponent. That means that function describes decay. But that 2 at the beginning of the function, that first term, tells us to shift the graph 2 units up. Alright? So let's graph the function real quick. That's the... So in this case, we need to shift that horizontal asymptote on the exponential function 2 units up. And since in this case, the bound, or rather the function behaves like this, what does that look like? Like a lower bound or like an upper bound? It looks like a lower bound, alright? So this is a lower bound, so this sequence is bounded below by m, little m, by the way, because lower bound we use lowercase m, and for the upper bound we're going to use uppercase bound.
Why are we finding the limit of 2 plus b so like the original function is 2g?
Oh, well, that's, okay, so this is going to be 0?
Yeah, but the original function is 2 times.
No, there was a typo. Yeah, there was a typo here. For some reason, I forgot to type the plus symbol here. So this is the actual one. All right. So let me cross it out because there was a little typo. All right. Okay. So it's bounded below by little m equals to 2. Yes.
Why is it bounded?
Because that limit is below the graph. So this is the graph of the function related to the sequence, and that limit going to infinity, well, that limit is it's asymptotically under the graph. Okay. So let's look at letter B, arctan pi n. So limit arctan of pi n as n approaches infinity. All right. What is this limit equal to? Where is arctan going to for large values of n? At infinity. It's pi over 2, right? However, that doesn't tell us anything about whether this bound is an upper bound or a lower bound. So how about we look at the graph of arctangent of pi x. So f of x equals arctangent of pi x, and recall, well, we already reviewed this graph back when we covered, what was that, improper integrals to determine the behavior at infinity. And recall that this graph has two horizontal asymptotes, one at negative pi over 2 and one at pi over 2. And be careful here because the graph is showing us two horizontal asymptotes, and both of horizontal asymptotes are number one, the bound above and the bound below. However, in this case, the tricky part might be that we can list this as bounded both above and below. However, look at the region that we're interested in. We're only interested in the positive side of the function. We don't care about the negative side. So if we care about the positive side of the graph, that is for n equals 1 all the way to infinity, so that part has an upper bound in this case, all right? And in this case, we say that this is bounded above by big M. In this case, because it's an upper bound, we use uppercase M equals to pi over 2. All right? Let's look at one more example. Letter C. What about the sequence sine of pi over 2n? All right. Well, how does that sequence behave? Number one, how about we expand some of the terms of the sequence? Okay, so for n equals to 1, that's going to be 1 times pi over 2. But what's sine of pi over 2? 1, comma. N equals to 2, that's pi over 2 times 2. Well, that reduces to pi. What's sine of pi? And then 3 pi over 2. And then 0, 1, 0, negative 1. That's the pattern given by this sequence in here. So it would be great if we actually plot this sequence. Okay? That way we get a better idea of what's going on with the sequence right here. So 1, 2, 3, 4, 5, 6, well, just a few. And well, for n equals to 1, that's 1, then 0. I'm going to use a different color. So 1, 0, negative 1, 0, 1, 0, etc. Right? Well, what is that sequence looking like? Okay, so this sequence to me looks like it has both bound above and a bound below. All right? And it's bounded above. Well, what's the maximum value that the trigonometric sine function attains?
1.
What's the minimum value? Negative 1. So that function, or this sequence then, it's bounded. We don't say bounded above and below. We just say bounded. That should imply both above and below. Bounded between negative 1 and 1. So we write this as an interval, which is essentially, in this case, the range of the related function in this case. But well, we need to further split these two into, okay, below by and above by little m equals to negative 1 and big M equals to positive 1. All right? And this concludes this section right here. All right. Let's move on to the next section, 11.2. For 11.2, we will discuss something similar but not quite the same. Infinite series. Well, infinite series versus infinite sequences. Well, they look similar, but one prominent way to distinguish between them, well, it's the notation here. So you can identify a series from a sequence by observing this symbol right here, which is the uppercase sigma symbol or sigma letter from the Greek alphabet. All right? And well, what did we do with the sequences in the previous section? All we did is list the terms of the sequence, like listing the first term, the second term, the third term, etc., and separate those numbers or those terms by commas in this case. We didn't do anything else. I mean, like, we didn't add the numbers, or all we did in this case is figure out the pattern. Well, in this case, we were given the rule, find the limit to determine whether that sequence is going somewhere that is convergent, or else just will goes up to infinity, and therefore we say that it diverges. For a series, we're going to do something about these terms. What we're going to do, we're going to add these terms. This means, and this is what the symbol means. Sigma means add, or summation symbol. That's another way to look at the symbol, the summation symbol. All right. So here is the issue, So when it came to last section, we look at how the sequences converge or diverge, right? By finding the limit. In this chapter, we're going to do something similar. This section and on, whether the series converge or diverge. But in some cases, we will use a couple of techniques to determine whether an infinite series, whether we can find the infinite sum, like 1 plus a half plus a 4 plus 1/8 plus. So suppose we're adding infinitely many numbers. Well, practically we cannot sit down and add infinitely many numbers and then obtain something. No, so there's techniques to do that. And the general technique which we will describe here, as a bigger picture, it's a pretty straightforward way to treat the problem. However, it may get crazy to the point that it's actually impossible to determine a pattern, so we can find the infinite sum using the limit of the sequence of partial sums. All right. So what are these partial sums? So every series has an associated partial sums, sequence of partial sums. For example, S sub 1. This S sub 1 right here, it's only the addition of the first number. There's really no addition. All we do is list that term. Done. S sub 2, that means the addition of the first two terms in the series, A sub 1 plus A sub 2. S sub 3, that means the partial sum including the first three terms of the series. In other words, add A sub 1, A sub 2, A sub 3, etc. S sub 4, add the first four terms, and S sub 5, add the first five terms, and so on and so forth. That's not a big deal. We can do that. We can just expand a few terms in the series, add them. But the problem, what makes it potentially an impossible task, is the next part, the next and last part, which is trying to figure out a pattern to turn that sequence of partial sums into a general rule to find a limit at infinity to get the infinite sum. And we're going to do one example, pretty much like the long way, just to show you, just so you can see why is this not a feasible task. And for this reason, from this section and on, we will just care about whether the series converges or diverges, right? Not the actual infinite sum. If this task of obtaining the general rule for the sequence of partial sums were an easy task, every single calculus book would only have two sections in the infinite sequences and series. The first section, infinite sequences, which you already did, and another section on infinite series, and do all this. But because this could be practically impossible, all we care is about determining the convergence or divergence of the series. And for that, we're going to look at different forms of series that are going to look like alternating series, that are going to get really crazy, that we can compare with other series, and many other techniques. So this is the reason why pretty much every calculus book has like 11 or 10 sections in this whole chapter, and not just two. All right, let's have a look at some examples. And worth mentioning is that there's only two special cases of forms of series for which we can obtain that infinite sum. And one of them is the telescoping series, and the other one is the geometric series, which we will describe in detail shortly. In the meantime, let's look at one example, the brute force way, if you will. All right. So essentially, we're trying to find the infinite sum of 1 over 2 to the n. Well, let's expand some of the terms to get an idea of what we're doing. In this case, well, 1 over 2 to the n starting at n equals 1, that's 1 over 2 to the first power, which is 2, plus 1 over 2 to the second power, which is 4, plus 1 over 2 to the third power, which is 8, plus 1 over 16, plus 1 over 32, plus 1 over 64. Well, we don't need that many terms. So just so you can see the pattern here, we might need a few more terms later. And again, this is the first term, a sub 1, second term, a sub 2. Yes.
Could you write that as 1 over 2 to the n?
Yes.
Just take the n out, because 1 over 2 to the n is 1 to any power is going to be 1.
Exactly, and that's what we will have to do later in the section when we cover the geometric series test. Thank you. This is not a, by the way, this is not a finite sum. This is an infinite sum, so plus dot dot dot, all right? So we need to give this a sense of infiniteness, if you will, all right? Well, so number one, let's start with finding the partial sum. Partial sums. So for the partial sums, let's denote number one s sub 1. And well, s sub 1 is just the addition of the first term, but come on, that doesn't take any addition, it's just listing, it's really listing the first term. Now, s sub 2, that's the addition of the first two terms, in other words, 1/2 plus 1/4. And I really don't want to spend too much time finding LCDs and all that, so I'm just going to give you the answer to this. So that's going to be 3 over 4. What about s sub 3? That's the third term, or rather the partial sum involving the first three terms. That's a 1/2 plus 1/4 plus 1 over 8. And combining these numbers together, again, I don't want to do too many LCDs and the like, that should be 7 over 8. And s sub 4, that's actually 1/2 plus 1/4 plus 1/8 plus 1 over 16. And well, that equals to 15 over 16. All right. I don't think we need too many. We need many more, any additional partial sums. 4 is good enough. All right. And well, I'm just giving you the answer to every single calculation. Think about how tedious it is to find LCDs or even typing these numbers in the calculator, right? So this is the sequence of partial sums associated with this infinite series. So S sub n, here is the tricky part. Here is what makes potentially an impossible task to do for every single series in the world. So this one is, trust me, this one is the easiest case. It's the easy one. All right. Well, so S sub n. So that's S sub 1 plus S sub 2 plus S sub 3 plus S sub 4 plus dot 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 to denote that we're going to have n terms or infinitely many partial sums by continuously adding the first 5, the first 6, the first 7, etc. But 4 is more than enough. All right, S sub n. So S sub n, which is S sub 1, which is 1/2, plus S sub 2, which is 3/4, plus S sub 3, which is 7 over 8, plus S sub 4, which is 15 over 16, plus infinitely many terms. Now, well, this one is not going to be as bad as it looks. So in this case, we need to find the general rule in terms of n. Remember what we did back in sequences when we were given the terms of the sequence and we were asked to find the expression that generates these terms. And again, in those situations, it's important to consider powers, the sequences of perfect squares, the sequence of odds or evens, powers of 5, powers of 3, powers of 2. So do we have any pattern that looks like that?
2 to the n minus 1 over 2 to the n.
So the denominator looks like 2, 4, 8, 16. Well, that's pretty much the same as in the original problem. So that one is easy to figure out. However, the tricky one might be the numerator, because between 1, 3, 7, 15, there doesn't seems to be an evident pattern, right? So in this case, we need to play a little bit with the numbers. How about maybe redefine these numerators in the following way? How about, well, how can we get this one? Isn't it the same as saying 2 minus 1, 3, 4 minus 1, 7, 8 minus 1, 15, 16 minus 1? And again, observe these numbers, 2, 4, 8, 16. They're the same as their denominators, 2, 4, 8, 16. All right? Do you see how tricky this part is? And guys, trust me, this is an easy one. So for this reason, we don't do this process to every single series in the world. In fact, like I mentioned before, all we are going to care from now on is whether the sequence only converges or diverges, and not trying to figure out the sum, except for except for a couple of cases. So 2 to the n minus 1. All right. So yes, we made it. We made it. So that means we can find. So the sum, the infinite sum n equals 1 to 0 or to infinity of sum a sub n equals the limit of the sequence of partial sums as n approaches infinity. So doing this, it's going to give us the infinite sum. So this means for our problem, sigma n equals 1 to infinity of 1 over 2 to the n equals the limit of the sequence of partial sums associated to this series, which we found in the previous step. And let's figure out this limit. So there's a couple of ways to go about it. Number one, well, direct substitution, infinity over infinity, because, well, that's 2 to the infinity, 2 to the infinity. This would be an indeterminate form of the indeterminate form, infinity over infinity. This means we can go about some algebraic techniques to go about this, to compute this limit, or L'Hopital's rule, or anything you can think of. All right, but I don't think L'Hopital's rule is really needed, because even though that the L'Hopital's rule will zero out the negative one, everything is going to get reduced. That's fine. However, an easier way to go about this one, that's limit 2 to the n over 2 to the n, that is split the denominator. And, well, 2 to the n divided by itself, this is 1 minus 1 over 2 to the n. As n approaches infinity, where is this second term going to go to for n equals infinity? 0, right? So that is 1 minus 0, that's going to be 1. And that's the infinite sum. Alright, that's the value of the infinite sum. This means that if we keep adding numbers to our series here, that is 1 over 128 plus 1 over 256 plus dot dot dot. If we sit down and count infinitely and add infinitely many numbers, this sum will be equal to 1. Yes?
When you have S a value up there, why is it 1/2 plus 3/4 plus 7/8?
Oh, this is the S sub 1, which is 1/2, S sub 2, which is 3/4, S sub 3, which is 7/8, and S sub 4, which is 15 over 16. It's the sequence of partial sums. That is the addition of the first term, the addition of the first two terms, the addition of the first three terms. And if we collect them together, figure out a pattern, that gives us the infinite sum. So, as you can tell, it's not an easy task, despite how easy this problem is it's tedious, and this part especially, it could be the trickiest part when you have to like break up the numbers, or play with the numbers to express them in a different way. Yes.
Isn't that like, I forget what it's called, but it's like where you have the limit as n approaches infinity and you have the general solution to n minus 1 over 2n. Can't you put like absolute value bars and then it would be like times 2 over n plus 1 over 2 to the n and like try to like, that's like less than 1 and like try to factor out that way or something like that?
Well, so those absolute value bars are coming up in the geometric series when we identify that common ratio. So, but yes, you actually no, that's not the upcoming topic yet. First, we're gonna look at the telescoping, and then we'll look at the geometric part. All right. The first series that we're gonna look out of 10. Well, actually, we're skipping one. We're skipping the root test for some reason. So we're going to do the telescoping series, which has this form: b sub 1 minus b sub 2 plus b sub 2 minus b sub 3 plus b sub 3 minus b sub 4, and so on and so forth. Why is this called a telescope? Well, a telescoping series, because this looks like using a telescope, Well, notice how b2's cancel, b3's cancel, b4's cancel, b5's cancel, b6 cancel, b7, etc. So when we're using a telescope, so the telescope user is in the initial position. So you use the telescope and you want to look, I don't know, maybe 20 miles away from you without caring about what's in between. So your objective is 25 miles or 15 miles, right? So that's why you don't care about what's going on in the middle. So those terms get canceled, they don't matter. So that's why we call this a telescoping series, because that's the analogy, if you will. All right. Well, so telescoping series usually have the look of rational expressions. In some cases, they would be nice to you and give you the rational expressions already broken up. In some other cases, you will be given a single rational expression. You would have to go about the partial fraction decomposition process. All right. So in this case, we were given a nice and easy one. So how is that going to look? So in a way, we're going to do another sequence of partial sums, if you will, but something different is going to happen here. So let's see. So number one, I'm going to write down the series again. Sigma n equals 1 to infinity, 1 over n minus 1 over n plus 1. And that equals to, for n equals to 1, for n equals to 1, n equals to 2, n equals to 3, n equals to 4. So we're going to expand the series only a couple of terms. All right? And so that's going to be, okay, so that's 1 over 1, which is 1, minus 1 over 2 plus 1 over 1 plus 1, which is 2. All right? Plus n equals to 2. 1 over 2 minus 1 over 2 plus 1, which is 1/3. Plus n equals to 3. So 1/3 minus 1 over 3 plus 1, which is actually 4. Plus 1/4, I think you see the pattern here. 1/4 minus 1/5. And then, well, this series is going to continue forever, pretty much. All right? So this is going to go plus dot 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 plus, okay, in the end we are going to reach the nth term, your favorite n, infinity or whatever it is. So that n term is again, okay, I'm going to leave a space for something here, 1 over n minus 1 over n plus 1. The second to the second to the last term would be, okay, minus 1 over n. All right, so this is what's going to happen. By the telescoping idea, the negative 1/2 cancels the positive 1/2. The negative 1/3 cancels the positive 1/3. The negative 4th cancels the positive 1/4. The negative 1/5 cancels the, well, we would have the positive 1/5. And then negative 1/6, positive 1/6, and then negative 1/7, positive 1/7. We don't have to do this forever. So we can focus on the first couple and the last of them. In this case, notice how the 1/n cancels with the previous one, which is negative 1/n. And this would be whatever that term is canceling. So we will only focus on the surviving terms. So the surviving terms are, again, the first one and the last one. Just like the telescope, you are in the initial position and your objective is what you would see in the telescope, which in this case is the last term. Alright? So this is 1 minus 1/n plus 1, and if we compute this infinite sum, the limit, this is actually the infinite sum. S of n approaches infinity, that's the limit, n approaches infinity of 1 minus 1/n plus 1. And notice how this term is going to go to 0, because 1 over essentially is 1 over infinity, 1 over really big, that becomes a 0. And 0 plus 1, that's 1. So the infinite sum is 1. This concludes the telescoping series. Let's get to the geometric series. And a geometric series is a very, very special sequence or series, if you will. Well, we're going to focus on the series part of the geometric one. So it has this form: a times ar times a times a plus ar plus ar squared plus ar cubed, etc. But what's this? So consider this sequence of numbers right here. So 2, 4, 8, 16, 32, all right? And well, a geometric series is distinguished by having the same ratio when you compute the same value when you compute the ratio of a term and between one term to the previous term, for example. So what's the ratio here? What if we divide 4/2? What's the answer? What about 8/4? What about 16/8? What about 32/16? Also 2. So we have a common ratio, right? When we divide a term by its previous one. This means that we can actually write this sequence of numbers in this format because, for example, this 2, that's 2 times 2 to the 0 power. That's 2 times 2 to the first power, 2 times 2 to the second power, 2 times 2 to the third power, 2 times 2 to the fourth power, and this is the form a r to the n power, a r to the n power, a r to the n power, where that value of r is always the same, that value of a is also always the same, but what changes is the power of r. Alright? So that's how we distinguish a geometric series, but be very, very careful when working with geometric series. This is key. If you don't make sure that about this piece of information, you would be doing the incorrect calculation of a sum. So this is the form sigma n equals 0 to infinity. This series must start at 0. So write it as a special note. Must start at n equals to 0. Alright? Otherwise, if the series is not starting at n equals to 0, we need to do something called shifting of indices, which is something we will cover next time. Alright? So if it's in the index n equals to 0, that's we will be able to use this formula to get that value of the infinite sum. And this is one of those cases in which it's possible to find the infinite sum. This one and the previous one, the telescoping one, all the series that we're going to look any further, we're just going to determine whether they converge or diverge. Alright, so let's look at sigma n equals 0 to infinity of 1 over 2 to the n. Well, number one, unfortunately, this series is not yet in the correct form, in the form a r to the n power. So we need to do the following. We write sigma n equals 0 to infinity. That's the same as saying 1/2 to the n power, and I left a space on purpose so you can see that there's indeed an invisible 1 in here. Alright? So we need to identify the parameters of the series, and the two parameters are number one, a, which is the first term of the series, and r, which is the common ratio. Let's list them. So a equals to 1 and r equals to 1/2. So we're going to judge the series by its value of r. So and that's to determine whether the series converges or diverges. So we're going to take the absolute value of r. That's absolute value of r, which is absolute value of 1/2. And what's the absolute value of 1/2? It's 1/2, right? Now the question is the number 1/2 less than 1 or greater than 1? Greater than or equal 1? It's less than 1, alright? Less than 1. So for this reason, we say that the series converges. And because of the geometric series, when it comes to converging, we may go about computing the infinite sum using this formula right here. Alright? So that's S infinity equals A over 1 minus R, where A equals to 1 over 1 minus 1/2. Well, what's 1 minus 1/2? Isn't that 1/2? And 1 divided by 1/2, isn't that 2? So that's the infinite sum. That if we sit down and add 1 over 2 to the first, plus 1 over 2 to the second, plus 1 over 2, etc., infinitely many terms, eventually we should get a 2. Let's do one more. One more, I'll tell you a joke, and then we call it a day. Alright? So, letter B. We have a series here, a geometric series, and well, we can tell by the form. In fact, for this one, we don't have to do anything about it because we can tell right away what our A is, which is 3, and we can tell what our R is, which is 5 over 2. Let's determine whether the sequence converges or diverges by taking the absolute value of R, and in this case the absolute value of R, which is absolute value of 5 over 2, which is 5 over 2. Now, is 5 over 2 less than 1 or greater than or equal to 1? Greater than or equal to 1. For this reason, the series diverges. Alright? So what's the joke? Well, so that first example reminds me of a math joke. And so there is this bar, and then a mathematician walks into the bar and orders 1 beer. Then another mathematician walks in and orders half of a beer. And then a third mathematician walks in and orders 1/8 of the beer. And then the bartender goes like, okay, hold on. He serves 2 beers and he goes like, you guys help yourselves. All right.